So last time we ended up by just saying, just stating Bregman's theorem, which says, okay, so if G is a bipartite graph with bipartition AB, so PM of G is just shorthand for the number of perfect matchings in G. And we're trying to prove an upper bound. So we want to say, if I have a bipartite graph, what's the maximum number of perfect matchings I could have, sort of as a function of the degree sequence in some sense. I mean, specifically, it's just to say if G is deregular. So deregular bipartite graph, how many perfect matchings could you have? And this is, so Bregman's theorem, it works for much more general cases than just deregular. But in particular for deregular, it says that the perfect number of perfect matchings is at most d factorial n over 2d to the power of n over 2d. And we saw that this is optimal by taking copies of KDD. So if I take, so this is bipartite deregular n vertices, right, as usual. If I take n over 2d copies of KDD, that gives me a tight example. But actually, if you look at the general Bregman's theorem, if I take, say, if I take, you can actually take different complete bipartite graphs as long as they're balanced. So if I take k d1, d1, and then a different d2, d2, such that, and dot, 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 such that all of the, so the number of vertices in each of these is 2 times di. If that adds up to n, then, or whatever, it doesn't matter what it adds up to, but in any case, Bregman's theorem is tight for all of these types of examples, if you check. Okay. Okay, so it's kind of a strange, to be honest, this thing on the right-hand side is strange, but it's kind of, I find it kind of amazing that we can prove any kind of upper bound that looks that strange. Yeah. Oh, sorry. Yeah, Bob. Okay, so then you might have had a 1/5 instead of a 1/6. Okay, so what we're going to do is prove this Bregman's theorem using entropy. So actually Bregman proved this, before, earlier with some other argument, which I have no idea what it is. I'm pretty sure the paper's in Russian. I can't remember, but I think it's in Russian. The proof I'm going to give here is a much more modern proof due to Radhakrishnan. And basically, it's all just involving these facts about entropy that we learned about last time. Okay, so let's go right into the proof. So let G be a bipartite graph with bipartition AB. And suppose I take I don't even know. So if G has no perfect matchings, then it has 0 and the bound holds, so that's fine. So assume that G has at least one perfect matching. And suppose that I pick one. So I just put all the perfect matchings of G into a bag, and I pick one out at random. And I call it M. So what is the entropy of M? And it's not going to be possible to write down some sort of exact or some sort of numerical formula for this, but, in terms of the graph G somehow, what is H of M? My Zoom seems to be having some problems, but, oh, here it is. Well, so the thing here is that we're picking it uniformly at random. So remember, if you have a set of n things, and I'm picking one uniformly at random, so just you have n things and you're basically picking them out of a hat, the entropy is always log of the number of things. So here, M is a uniformly random matching, so it's just going to be log of the number of perfect matchings. And let's say log base 2 of the number of perfect matchings in G. So that's just by the fact that, uniform random variables, the entropy is just the log of the size of the range. And the range here is all the perfect matchings, so and they're all equally likely, so we have this. What we're trying to do is get an upper bound on this, the perfect number of perfect matchings. And so it suffices to prove an upper bound on the entropy of M, because if you prove these things are equal. So if I prove that H of M is at most the log of the upper bound we had on the previous slide, so that one, or maybe 2 slides ago, that one. If we prove H of M is at most the log of this, then we'll have that number of perfect matchings is at most that thing. So everything comes down to bounding the entropy of this random perfect matching. Okay, so remember, throughout this, remember M is a random perfect matching. So for each vertex, I kind of generate my random perfect matching. It's a bunch of edges. And that kind of gives me, for each vertex of the graph, I can say, okay, what is the vertex that V gets matched to? So remember, this is a perfect matching. So every vertex of the graph gets matched to some other vertex. So for each vertex, I can let X of V, or X sub V, the vertex that V gets matched to. Okay, so the picture is kind of like this, right? I've got this graph. I've got the red edges are a perfect matching. I've got V here, and X of V is the thing V gets matched to. And just a kind of observation that if I know, suppose I tell you, like, for each vertex of A, I tell you who or which vertex that it gets matched to. So for each V in A, so just on one side of the bipartition, I go through each vertex of A, I tell you XV for each V in A, then that completely determines the matching, right? If I just say for each vertex in A, who did you get matched to, that is equivalent to M, basically. So it should have the same entropy as M. So the tuple, so that's just kind of a basic observation. But the good thing about this is this is going to allow me to use my kind of conditional entropy thing where I can pull things apart, because this is like a tuple. Like if you think of these vertices as being labeled 1 up to something, I can make up the entropy of this tuple in terms of the individual components with conditional entropy going on. Okay, so am I going too fast, or is this okay? Okay, so suppose I fix an ordering of A. Okay, usually N denotes the number of vertices in the whole graph, but let's just say, right now so the vertices of A, I call them V1 up to Vn. Let's say that the size of A is N. Okay, so what we've said is that the log of the number of perfect matchings is equal to, it's equal to the entropy of M, the random matching, which we said is equal to, so it has the same entropy as just knowing the tuple, like xv1, xv2 up to xvn, because knowing everybody in A gets matched to is the same as knowing the matching. And if I kind of use this specified ordering, and I use one of these facts about entropy we talked about last time, we can break this up into a sum of kind of individual, for kind of focusing on individual vertices. But the kind of annoying thing is you have to do this conditional entropy thing. Kind of the amount of information I get from learning xv for all V in A is the same as learning like who V1 gets matched to, and then the amount of information you learn from seeing who V2 gets matched to, given that you already know who V1 gets matched to, and then V3 given V1 and V2, and then V4 given 1, 2, 3, and so on and so forth, all the way down to the last vertex Vn given all the previous vertices. So this is just by the thing about entropy of a tuple of variables, right? That you can split it up into the constituent parts, but you have to have this kind of conditional entropy thing. Okay. So here's a question. What is the range, or maybe what's an upper bound on the range of xv1? So remember, x sub v1 is the vertex that v1 gets matched to in a random matching. So how many possible choices are there for xv1, x sub v1? I would go smaller than that. So something depending on v1, I would say. But certainly there's at most n of them. Yeah. But totally, yeah. And a kind of hint that that's where we want to go with this is that, like, we want some upper bound on the entropy involving all the degrees of vertices in A. Remember, V1 is like the first vertex in A or whatever. And yeah, the number of choices, so the range of x sub V1, so x sub V1 is the vertex V1 gets matched to. The size of the range of this is at most the degree of V1. It's possible that it's smaller because there might not actually be, like, for some choice of neighbor of v1, if I try to put that matching edge in, it might not actually extend to a perfect matching. Like it might be impossible for v to be matched to certain neighbors, but certainly there's fewer, at most that many choices for xv1. Yeah. Yeah. Well, yeah. Yeah, exactly. If the neighbor if a given neighbor of v1 is adjacent to a leaf on the other side, then that matching edge has to be there, and so v1 to that one can't be there. So that's actually a good example. That's a nice example. Okay, so right. So then that gives anyway. So even though this might not always be a good bound, it does give me an upper bound on the entropy that it's at most. So if I just look at that vertex individually, it's at most the entropy is at most the log of the degree of v1, because it can only take that many different values at most. The degree, many values. Things become trickier when I say I want you to kind of figure out, like, suppose I have already chosen. So imagine I'm revealing this perfect matching kind of vertex by vertex in terms of like the vertices of A. I reveal the neighbor of v1 in the matching. And then I ask you, okay, how many choices are there for x sub v2, so the neighbor of v2 in the matching? And well, it's one of two different cases, but you can't just write it down like without thinking of who v1 gets matched to, because I mean, if v1 gets, if the picture looks like this, that v1 gets matched to some vertex here, and so suppose this is the neighborhood of v2. If that's not in the neighborhood of v2, so in that case, v2 has degree of v2 choices, right? But if v1 happened to be matched to a neighbor of v2, then things are different, right? In this case, v2 has degree of v2 minus 1 choices, because one of them is taken. Is that clear? You could upper bound in that way. In that case, what you would end up with, though, is in this factorial, you'll end up with like degree to the power of the degree or something. It's not going to give you as good of a bound. But yeah, you could throw things away and kind of think of this. But if you think about our tight example, so imagine just KDD. In our tight example, actually, when I suppose, so not components of KDD, but just a single KDD, when I choose the first one, it always affects the choice of the second one. So kind of in our tight example, we're always in this case kind of thing, right? So we want to be able to kind of exploit this case, actually. And yeah, we want to exploit this, like, because this gives us smaller entropy in some sense, that if V has fewer choices, that gives us a better upper bound. And we want to be able to use that somehow. So this is where things get, a little bit, it's tricky to come up with the idea, like, how am I going to fix this issue that I don't know how to take advantage of, of these different possibilities, right? So, okay, so this is just, anyway, I don't perhaps need to say this, but like, in general, if I've already chosen the first I minus 1 are revealed, the number of possible choices for the neighbor of VI is like all the neighbors that VI has left that haven't been chosen yet by one of the ones that came before VI. But yeah, I think that's kind of clear. So here's the thing: our ordering of A was arbitrary, and if if you don't think about how to choose the ordering, then it's going to be really complicated. But actually, things become easier if you kind of look at all the possible orderings and you kind of add this thing up over all of these orderings. So A has n elements. There's n factorial ways to permute the elements of A. And I kind of imagine I like look at all of those different ways of kind of ordering the elements of A. And I write out this expression for all of them. So actually, this kind of connects to something that we were kind of talking about last time, this weird thing that if I take a pair of random variables like x1 and x2, pull them apart in either different order, right, given x1, and these are going to be the same, plus h of x1 given x2, even though the constituent parts are not the same. So the entropy of x1 might be different from the entropy of x2. X2 given x1 is probably different than x1 given x2, but it's still equivalent to write it in any of these different ways. So So basically what we're going to do here is we look at all the possible orderings of A. There's n factorial of them. You could think of writing this equation that we had before for all of those different orderings and adding them all up. So formally what this gives you is that n factorial times the log of the number of perfect matchings, because we're adding it up n factorial times. And on this side, we have a sum over all the different permutations of 1 up to n. And we can kind of write this in terms of our initial ordering. So we just kind of apply pi to the initial ordering. So it's like the entropy of x sub v pi of 1, and then pi of 2 given pi of 1, pi of 3 given pi of 2 and pi of 1, and so on and so forth. And somehow this, by summing over all of the orderings, this is actually going to get rid of this problem about not knowing how many of your neighbors are left to choose. So because, well, this is the tricky part to explain, but, well, imagine just this situation. Well, okay. In some sense here, in half of the orderings, V1 will come before V2, and in half of the orderings, V2 will come before V1. Well, okay, no, this is, perhaps this example isn't the best to think about. Let me actually, stay on kind of script here. Right. So here's the reason why summing up over these different orderings helps. Imagine I've got a vertex V, which has degree D, and V is in A. So in any perfect matching, I know that V gets matched to somebody here, and I know that all the rest of the vertices in the neighborhood get matched to other vertices in A. Now, when we come to, so remember, we're kind of randomly permuting the vertices of, or we're doing all the permutations of vertices of A, and then kind of revealing them one by one, or revealing who they're matched to one by one. If you kind of fix the matching, then there's going to be so if I look at the neighbors of V and I look who got matched to them, there's V plus there's D minus 1 other vertices. So in this case, maybe D is 4, so there's 4 vertices that get matched to the neighborhood of V. If I look over all the orderings, and I look at, for example, I look at the orderings where V comes first among these 4. So you can think of V as being Bob and these being his friends in some sense. So this, we're looking over, if you think about all the orderings where V comes first among these 4, at that point, when you reveal the edge or the neighbor of V that's in the where that edge is in the matching, at that point, V had 4 choices. And that's going to happen a quarter of the time, because when I say quarter of the time, I mean for 1/4 of the number of permutations of A, V will come first. And in all of the ones where he comes first, when you go to reveal its edge, it has 4 choices. Whenever it comes second among these 4, when you go to reveal its neighbor in the matching, it has 3 choices. If it comes last, it has 1 choice. If it comes second to last, it has 2 choices. And all of those different scenarios, like where it comes first, second, third, or fourth, each of those happens kind of a quarter of the time, in terms of, for a quarter of the different permutations, V comes first among those 4, and for a quarter it comes second, for a quarter it comes third, for a quarter it comes fourth. Okay, so somehow by summing over all the different permutations, it kind of smooths everything out. And kind of, you can kind of say how often V has how many choices. Right. So this is kind of a complicated way of saying this algebraically, but so this is what we had before, and this is like an extremely long, thing to go below a sum, but is right. If I kind of change the order of summation in some sense, how do I explain this? So I've got all the orderings here. And then sort of within each ordering, I'm doing some sort of sum over all the vertices one by one. Now I want to kind of reverse that somewhat and say I want to sum over all the vertices in A. And then I want to say, okay, if I look at so now I want to sum over all the permutations. And specifically, I want to kind of break up the permutations. So I've got a vertex V in mind. So I've chosen V here. And I can now break up the set of all permutations depending on where V comes in relation to the other vertices that get matched to the neighbors of V. So it either comes first, second, third, or all the way up to the last it could possibly be is the degree V among those vertices. Okay, so I defined this thing AV, which was, so that was on the previous slide. I didn't really mention it, but AV is the set of all W in A that gets matched to something. Let's say WU is in M for some U, which is a neighbor of V. So it's all the things that get matched to a neighbor of V, right? Might not be, to be honest, I might be kind of, I mean, AV is a random variable. I might be kind of, this might not be the most rigorous, this might not be completely a proper way of doing this. But essentially this is the idea that if I look at this set AV, so all the things that get matched to a neighbor of V, if V comes first among all the things in AV, then when you go to choose the edge coming from V, you have D of V choices. If it comes second, you have D of V minus 1 choices because one of them has already been taken. One of its neighbors has already been taken. Anyway, at the end of the day, what you get is that this expression here is that most log of the number of choices that V has, which given that there were K things before, basically K minus 1 of the neighbors of V are already taken, it's log of degree minus K plus 1. Yeah, so I might not be explaining this kind of in the most rigorous way. I feel like there's something slightly missing here, but this is the idea, that, yeah, so then you can bound this by log of the number of choices, and if K minus 1 of the choices are already taken, then there's D of V minus K minus plus 1 choices for the neighbor of V. Okay, so given that you can kind of make that part rigorous, you're done. So on the left side, we have n factorial times the log of the number of perfect matchings. On this side, we have sum over all the vertices. Yeah, the sum from K equals 1 to dV. And what was the role that K was playing? So in this innermost sum here, so we were summing over all the permutations where V is the kth element of this set AV. And if you think of this pole thing from before, if I take all the permutations and I say for how many of them is V the first one in AV, it's 1 over the size of AV, which is 1 over the degree of V, times the number of permutations. So that's where this n factorial over dV comes from. Okay. And then we had this log of degree minus K plus 1. The way that logs work is that, okay, so I'll take out this n factorial because why not? The way that logs work, right? If I've got 1 over dV here, I can take that inside and make it a power, right? And then I'm summing over all the K, and that becomes, summing logs becomes multiplication. It's a little hard to see this, but yeah, so I get, and then I sum over all the vertices, and that becomes, so this sum here becomes this product, because that's how logs kind of work. Sums become products. This thing becomes this exponent, and the sum from K equals 1 to dV is multiplying all of these over all K, which gives you d of V factorial, which is there. We cancel the n factorials and take both sides, take 2 to the power of both sides to get rid of the logs, and you have the number of perfect matchings is at most the product over all vertices in A, d of V factorial to the 1 over d of V. That's kind of a tricky one, but yeah, that's the idea. So that's one of these. I think it's a beautiful result, to be honest, and I think it's amazing how, to be honest, like, so there is a little bit of thinking about this whole thing about going over all the orderings, and how that works and why that gives you something like this. But apart from that, it's all just using these basic facts of entropy. And yeah. One thing I wanted to say is that this Bregman's theorem is actually equivalent to something which seems different. So has anyone heard of the permanent of a matrix? Yeah, so there's the second proof of Shriver that came later, right? So yeah. But then Radhakrishnan, so this is, I mean, all of these proofs are probably similar, but in some sense, in some high level sense, but yeah, Shriver gave a second proof. Okay, so the permanent of a matrix. So basically the permanent of a matrix is like kind of almost the same thing as a determinant, except in a determinant there's some sort of -1 thing. But let me kind of tell you properly what the permanent is. So suppose I have an n by n matrix A. So then the permanent of A is defined as follows. So you sum over all the bijections from n to n. And for each bijection, you compute the product. You compute the product of AI, what is this? Sigma. Sigma I over all I equals 1 to n. So if you take for example, if you take the identity bijection, so sigma of I equals I, this will take the product of diagonal entries, right? Then you take so you're going over all the different bijections and you're taking this product and you're adding them all up. I don't know. So there's different ways to compute determinants and stuff, but there's a formula for determinants which looks almost the same as this, where it's basically the same setup, except that there's like this -1 to the, and I might have this wrong, but to the like sign of sigma or something, like meaning if sigma is an odd permutation, you do a 1. If it's even, you do a -1 or something. I might even have that backwards. But this is kind of like a determinant without the -1 thing. And it's generally quite hard to compute the permanent of a matrix, interestingly. Even though the determinant can be computed quite quickly using, like, I don't know, Gaussian elimination or something like that, the permanent is harder to determine. And actually, this whole thing about bipartite graphs and matchings actually gives us an upper bound on the permanent of a 0-1 valued matrix. And here's how that works. So if I take a bipartite graph with bipartition AB, I can turn that into a matrix. So I don't want to take the adjacency matrix. So that's one way to turn a graph into a matrix. But for a bipartite graph, you can do it kind of in a simpler way by taking a so-called bi-adjacency matrix. So for the bi-adjacency matrix, in an adjacency matrix, you would have column, V of G rows and V of G columns. Bi-adjacency matrix, the difference is that you have like A rows and B columns. And so these correspond to the vertices of A, these correspond to the vertices of B. And in a given box, you put a 1 if the corresponding vertex is adjacent to the other so the corresponding vertex of A is adjacent to the vertex of B, corresponding to that column, and you put a 0 otherwise. So it's sort of like the adjacency matrix, except that in a bipartite graph, you don't have to store the data about A cross A because there are no edges in A, there's no edges in B. So you just have to talk about edges from A to B. And it's actually pretty easy if you look at the definition of the permanent. So PER means the permanent of the matrix. That if G is a bipartite graph, then the number of perfect matchings in G is just equal to the permanent of the bi-adjacency matrix. And yeah, so any bi-adjacency matrix corresponds to a bipartite graph. So this thing I did before is like reversible, right? So really 0-1 valued matrices are like in a 1-to-1 correspondence with bipartite graphs. And yeah, the permanent, so the number of perfect matchings in G is just equal to the permanent of B of G, where B of G is the bi-adjacency matrix. And if you kind of think of it, like, it's because you can think of these bijections as saying, like, the ith vertex of A gets matched to the sigma of I vertex of B kind of thing. But if there's no edge between the ith vertex and the sigma ith vertex, and then this will compute a 0, so that matching will count 0 times. But if there's an edge between every pair that you're trying to match, it'll give you a 1. So it'll count 1 for every perfect matching. It'll count 0 if it ever chooses a non-edge, in some sense. Okay, so long story short, Bregman's theorem implies that if B is a 0-1 valued n by n matrix, then the permanent is at most product I equals 1 to n, so of Ri factorial to the 1 over Ri, where the Ri things are the row sums. So Ri is the sum of the ith row of B, which kind of corresponds to the degree of the ith vertex of like A, where A is the, if you have a bipartite graph, A and B or whatever.